The universe is hiding secrets in plain sight. All across the cosmos, astronomers find things that simply should not exist according to the rules we know. These are space anomalies, phenomena that defy our current understanding of physics and astronomy. They are not mere curiosities. They are profound clues, each one a potential key to rewriting the scientific textbooks. Today, we embark on a journey through 25 of the most mind-bending cosmic mysteries, from a signal that screamed from the void only to vanish, to a star that dims in ways no planet ever could. By the end, you will see the night sky not as a static map, but as a living puzzle brimming with unanswered questions. What cosmic discovery, waiting just out of sight, would change everything you thought you knew? On a quiet August night in 1977, a radio telescope in Ohio known as the Big Ear was silently listening to the stars. It was part of a long-running search for extraterrestrial intelligence, a project that mostly recorded the cosmic background hiss of the universe. But on August 15th at 10:16 in the evening, the machine saw something extraordinary. For 72 seconds, a powerful, focused beam of radio energy slammed into the telescope's receiver. It was a narrowband signal, meaning it was concentrated on one specific frequency, just like a radio station you might tune into, and this was not just any frequency. It was precisely 1420 MHz, the natural emission line of neutral hydrogen, the most common element in the cosmos. Scientists had long theorized that any advanced civilization wanting to be noticed might use this universal channel as a cosmic hailing frequency. The signal was so strong that it overwhelmed the equipment. The next day, astronomer Jerry Amon was reviewing the computer printout, a long scroll of letters and numbers representing signal strength. His eyes landed on a single column of data. Where he expected to see a string of ones or twos, he saw the characters 6E, Q, U, J, 5. He circled it in red pen and wrote one word in the margin. Wow, the WOW signal, as it became known, was perfect. It had all the hallmarks of an artificial interstellar broadcast. It came from a point in the constellation Sagittarius near the center of our galaxy. And then, just as suddenly as it arrived, it was gone. Despite decades of searching with far more sensitive equipment, no one has ever heard it again. Over the years, many natural explanations have been offered. Could it have been a reflection from a passing satellite or space debris? The signal's characteristics do not match. Perhaps it was a comet. 2 comets were in the general area at the time, but they do not emit strong, narrowband radio waves at the hydrogen line. A pulsar, a spinning neutron star. Pulsars emit across a wide range of frequencies, not a single clean tone. Every proposed natural cause has crumbled under scrutiny. The WOW signal remains a singular event, a 72-second shout into the cosmic dark that we heard once and have never been able to answer. It stands as the most tantalizing, frustrating, and enduring mystery in the search for cosmic company. A ghost in the machine of the universe that whispers one unanswerable question. What or who was calling? That solitary, unanswered signal from the cosmos was just the beginning. While we were listening, another group of observers was watching, and they found something that defied every expectation of how a star should behave. Far from the mysterious WOW signal's origin point, in the constellation Cygnus, a star named KIC 8462852 began to act strangely. It was discovered by the Kepler Space Telescope, an instrument designed to hunt for planets by watching for the tiny, regular dimming that occurs when one passes in front of its star. But this star, soon nicknamed Tabby star after astronomer Tabitha Boyajian, did not dim in a tiny, regular way. Its light would drop by staggering amounts, sometimes by a full 22% before slowly returning to normal. A planet, even a giant one, would cause a dip of perhaps 1%. This was something else entirely. The dimming was erratic with no discernible rhythm. It would plunge deeply for days, then barely flicker for years. Citizen scientists from the Planet Hunters project were the first to flag the bizarre data, proving that sometimes the most revolutionary discoveries come from curious eyes sifting through the numbers. Astronomers scrambled for explanations. The first thought was a colossal swarm of comets, thousands of them, passing in front of the star. But to block that much light, the comets would have to be on an impossibly scale, and their tails would leave a specific infrared signature that we do not see. Then perhaps it was a thick disk of circumstellar dust, the leftover debris from a planetary collision. Yet the dust should scatter blue light more than red, and Tabby's star dims almost equally across all colors, which is deeply puzzling. Each natural hypothesis encounters a stubborn piece of data that does not quite fit. The strangeness of the observations inevitably led to a more speculative idea. Could we be seeing the shadows of an alien megastructure? The concept of a Dyson sphere, a vast swarm of energy collecting satellites built around a star by a civilization harnessing its total power, moved from science fiction into scientific conversation. While most astronomers consider this the least likely explanation, its very mention underscores a profound truth. Tabby's star is so bizarre that it forces us to contemplate all possibilities, even those that rewrite our place in the universe. It became a global phenomenon not because anyone believed in alien construction crews, but because here was a genuine cosmic mystery that no standard model could comfortably solve. Today, telescopes around the world keep a constant watch on Tabby's star, monitoring its every flicker. Each new dimming event is a fresh clue, a piece of a puzzle we are still assembling. It teaches us that sometimes the universe presents us with a phenomenon that is not just unknown, but seems almost engineered to be inexplicable, a celestial beacon that refuses to tell us its story. While Tabby's star presented a mystery of observation, a pair of human-made objects gave us a mystery of motion. The Pioneer 10 and Pioneer 11 spacecraft, launched in the early 1970s, were true trailblazers. Pioneer 10 was the first human-made object to travel through the asteroid belt and send back close-up images of Jupiter. Pioneer 11 followed, visiting both Jupiter and Saturn. After completing their planetary missions, they continued on trajectories that would eventually carry them out of our solar system entirely, becoming silent ambassadors drifting into the interstellar void. As they traveled, scientists used incredibly precise Doppler tracking to measure their speed and position by the faint whisper of their radio signals. Over years, a tiny discrepancy emerged. Both spacecraft were slowing down just a little bit more than they should have been. They were experiencing a constant, minuscule deceleration back toward the sun, as if an invisible, gentle hand was applying a tiny brake. This was the Pioneer Anomaly. The force was astonishingly small, about 10 billion times weaker than the gravity we feel on Earth's surface. But in the pristine, predictable environment of deep space, even a deviation that small is a glaring red flag. It was as if the universe's accounting books did not quite balance. The immediate suspicion fell on the spacecraft themselves. Could a tiny fuel leak from their thrusters be pushing them off course? Every possible ounce of propellant was accounted for, and the force remained constant long after any leaks would have stopped. Perhaps it was the pressure of sunlight itself, photons from the sun giving the craft a tiny push. Calculations showed this effect was far too weak. Maybe it was heat, the infrared radiation from the spacecraft's nuclear power sources acting like a weak rocket engine. For decades, this thermal explanation was the leading candidate, but proving it was a monumental task. The original engineers had retired, and the blueprints for the pioneers, with all their intricate details about how heat would radiate from their asymmetrical bodies, were not fully digitized. A team of researchers essentially had to become cosmic archaeologists, recovering old documents, memos, and even tracking down original parts to build a complete thermal model of the spacecraft. Their painstaking work suggested that heat radiating from the Pioneer power sources was not perfectly uniform. Slightly more heat was emitted from the back of the spacecraft's dish antenna than from the front. This anisotropic or directionally uneven thermal radiation could indeed produce just the right amount of tiny thrust to explain most of the anomaly. For many in the scientific community, this case was closed, a triumph of meticulous detective work over mystery, yet a sliver of doubt persists for some. The thermal model, while compelling, could not account for 100% of the anomalous drift with absolute certainty. That tiny, unaccounted-for fraction leaves the door open, just a crack, for those who wonder if we glimpsed something deeper. Could it have been a hint of modified gravity at the outer edges of the solar system, or a whisper of physics we do not yet understand? The Pioneer anomaly ultimately stands as a monument to scientific rigor, a reminder that the most profound cosmic secrets can hide not in distant galaxies, but in the millimeter-per-second drift of humanity's own creations, whispering a puzzle that took nearly 40 years to mostly solve. Just as the Pioneers drifted away with a lingering question, other spacecraft swinging past our own planet revealed a different kind of mystery. When a probe uses Earth's gravity for a slingshot maneuver, a flyby, its speed is predicted with incredible precision. Yet on multiple occasions, our best calculations have been wrong, as spacecraft like Galileo, near Shoemaker, and Rosetta whipped around our world. Deep space tracking networks caught something odd. Each one experienced a tiny, unexpected jump in velocity. It was as if, for a brief moment, the spacecraft received a gentle, inexplicable push. This is the Flyby Anomaly. The change is minuscule, often just a few millimeters per second added to a craft traveling many kilometers per second. You might think such a tiny error is trivial, but in the world of orbital mechanics, where a mistake of a single centimeter per second can mean missing a distant asteroid by thousands of miles, it is a glaring problem. Every variable is accounted for with extreme care: the mass of the Earth, the positions of the Moon and Sun, even the subtle pressure of sunlight on the spacecraft surfaces. After all that math, the speed should be exactly what the models say, but it never is. So what could be giving these probes an extra nudge? The first suspect was our own atmosphere. Even at altitudes of several hundred kilometers, wisps of the upper atmosphere could, in theory, create drag. But the anomalies were detected during flybys at over 1,200 kilometers high, where the atmospheric density is virtually zero. That explanation evaporated. Could it be the tides, the gravitational pull of the Sun and Moon subtly stretch and squeeze the Earth, which might slightly alter its gravitational field? Detailed models show this effect is far too weak. Some physicists have looked to more exotic ideas like frame dragging, an effect predicted by Einstein's theory of general relativity. A massive rotating object like Earth should ever so slightly drag the fabric of spacetime around with it, like a spoon spinning in thick honey. Could this be imparting the extra energy? Calculations suggest the frame dragging effect is about 100 times too small to explain the anomaly. We are left with a persistent, nagging inconsistency. Each new spacecraft that performs an Earth flyby gives scientists another data point, another chance to crack the code. The Juno mission to Jupiter had a perfect opportunity during its Earth flyby in 2013. Teams prepared meticulously, hoping to catch the anomaly in the act with modern instruments. Yet, to the surprise of many, Juno's speed matched predictions almost perfectly. This only deepened the mystery. Why does it happen sometimes and not others? Is it something about the spacecraft's trajectory, its shape, or its orientation? The Flyby Anomaly is a ghost in the machine of our own celestial backyard, a reminder that even the gravity of our home planet, something we think we understand completely, might still hold a tiny, untold secret. It proves that some of the universe's most confounding puzzles are not always in the distant cosmos, but right here, in the precise pathways we chart through the space around us. Gravity itself holds the most profound secret of all. Those tiny discrepancies in spacecraft motion are whispers compared to the cosmic shout emanating from every galaxy we observe. The universe, it turns out, is mostly made of something we cannot see. This is not a small oversight. It is a fundamental rewriting of cosmic composition. We call this elusive substance dark matter, and it represents the single greatest anomaly in modern physics. The evidence is overwhelming and comes from multiple, independent lines of observation. The first clue came from the way galaxies spin. Stars on the outer edges of spiral galaxies orbit the galactic center at astonishing speeds. According to the laws of gravity, these distant stars should be moving much more slowly, just as Pluto takes a sluggish path around the Sun compared to Mercury. The visible mass of a galaxy, all its stars and glowing gas, is simply not enough gravity to hold these speeding stars in their orbits. They should fly off into intergalactic space. The fact that they do not means there must be a vast, invisible halo of mass surrounding every galaxy, a gravitational glue we cannot see. This is the galaxy rotation curve anomaly. Then we have gravitational lensing. Einstein predicted that massive objects warp the fabric of spacetime, bending the path of light like a lens. When astronomers look at massive galaxy clusters, they see distant galaxies behind them stretched and distorted into arcs and rings. The amount of bending is far greater than the visible mass of the cluster can produce. An enormous amount of unseen mass must be doing the heavy lifting, warping space on a colossal scale. Finally, the afterglow of the Big Bang itself, the cosmic microwave background, bears the imprint of dark matter. The subtle patterns in this ancient light tell us how much total matter exists in the universe. When we add up all the atoms that make up stars, planets, and us, we account for a mere 15% of that total. The other 85% is the dark matter. So what is it? We know what it is not. It is not clouds of normal atoms, what scientists call baryonic matter. It does not emit, absorb, or reflect light. It does not interact with the electromagnetic force at all. It is utterly dark. It only makes its presence known through its immense gravitational pull. The leading candidate is a hypothetical particle known as a WIMP, a weakly interacting massive particle. As the name suggests, it would be heavy and would only rarely bump into normal matter, passing through our planet, our homes, and our bodies as if they were not even there. The hunt for these ghostly particles is one of science's grandest quests. To shield them from cosmic rays and other interference, detectors are placed in deep underground laboratories, in old mines or beneath mountains. They wait patiently for the once-in-a-lifetime ping, the minuscule recoil of an atomic nucleus if a WIMP ever grazes it. Meanwhile, particle colliders like the Large Hadron Collider attempt to create dark matter in high-energy collisions, hoping to see the missing energy it would carry away. This global search is a testament to a simple, staggering truth. The cosmos we see, with its glittering stars and majestic galaxies, is just the visible frosting on a cake made of something entirely unknown. Dark matter is the shadow framework of the universe, the hidden architecture upon which everything luminous is built. We live in a world dominated by a substance we have never touched, never seen, and do not yet understand. If dark matter is the hidden framework of the universe, then something else is actively tearing that framework apart. The discovery of dark energy was not just a surprise, it was a profound shock that overturned our most fundamental assumptions about cosmic fate. For most of the 20th century, scientists believed the universe's expansion, born from the Big Bang, was gradually slowing down due to the relentless pull of gravity. The only question was whether it would eventually grind to a halt or reverse into a cataclysmic collapse. Then, in the late 1990s, two independent teams of astronomers made a measurement that changed everything. They were using distant supernova, specifically a type called Aya, as cosmic mile markers. These stellar explosions have a known standard brightness, so by observing how dim they appear from Earth, astronomers can calculate their exact distance. By also measuring how much their light is stretched or redshifted by the expansion of space, they can determine how fast the universe was expanding when that light was emitted billions of years ago. The results were unequivocal and staggering. The most distant supernovae were fainter than expected. This meant they were farther away than our models predicted. The expansion of the universe was not slowing down, it was speeding up. Some mysterious, repulsive force was acting against gravity, pushing galaxies apart at an ever-increasing rate. This revelation earned the teams the Nobel Prize in Physics in 2011. We named this force dark energy. While dark matter pulls, dark energy pushes. And its dominance is absolute. When we map the cosmic budget of the universe, dark energy constitutes roughly 68% of everything. Normal atoms, the stuff of stars, planets, and life, make up a paltry 5%. Dark matter, for all its mystery, accounts for about 27%. This means over 2/3 of reality is composed of this accelerating force we cannot see or directly detect. The leading theoretical model for dark energy is Einstein's cosmological constant, a kind of energy intrinsic to the vacuum of space itself. Think of empty space not as truly empty, but as a seething quantum foam where virtual particles flicker in and out of existence. This quantum activity should give the vacuum a fundamental energy density, a constant pressure that drives expansion. There is just one catastrophic problem with this elegant idea. When physicists calculate what this vacuum energy should be based on quantum theory, the number they get is absurdly, impossibly large. We are talking about a value that is 1 followed by 120 zeros times bigger than what we actually observe. This is not a small rounding error. It is the single worst prediction in the history of physics. It is as if you calculated the weight of a feather and got an answer equal to the mass of the entire observable universe. This discrepancy is so vast and embarrassing that it screams we are missing something fundamental, a principle that reconciles the quantum world with the cosmic scale. Dark energy, therefore, is not just another item on a list of mysteries. It is the ultimate puzzle. It determines the final fate of everything. If it continues to dominate, it will lead to a cold, lonely, and isolated end for the cosmos, stretching the fabric of space so rapidly that distant galaxies will vanish from view, and eventually, even atoms will be torn apart in a distant future called the Big Rip. We are left staring into the void, knowing that the greatest force shaping the destiny of our universe is one we do not begin to comprehend. Even as dark energy pushes the cosmos apart on the grandest scales, a specific and powerful force is pulling us and everything in our galactic neighborhood toward a single point in the void. This is the Great Attractor, a gravitational anomaly of staggering proportions located roughly 250 million light-years away in the direction of the constellations Centaurus and Norma. Its influence is undeniable. Our Milky Way, along with the Andromeda Galaxy and every other member of our local group, is racing through space at over 2 million kilometers per hour, not just from the general expansion, but on a specific heading toward this mysterious focal point. Thousands of other galaxies are on the same cosmic current, all flowing toward a region of space that appears at first glance to be unremarkable. The mystery deepens because we cannot see it clearly. The Great Attractor lies directly behind the plane of our own Milky Way, an area astronomers call the zone of avoidance. Here, thick clouds of cosmic dust and billions of foreground stars create a visual smokescreen, blocking our optical view of the universe beyond. It is like trying to find a distant city while staring directly into the glare of a brilliant streetlight. For decades, this region was a blind spot on our cosmic map, hiding the source of the immense pull we could feel but not see. To penetrate this dusty veil, astronomers had to use different eyes. Radio, infrared, and X-ray telescopes can see through the obscuration, and they began to map what lay in the hidden depths. What they found was the Oumuamua cluster, a massive gathering of galaxies, and an even larger concentration of mass now understood to be the dense core of our home supercluster, which was given the beautiful Hawaiian name Laniakea, meaning immense heaven. This discovery was revolutionary. It showed that our Milky Way is not just a lonely island universe, but a suburban resident on the far outskirts of a vast filamentary supercluster of 100,000 galaxies, all bound together by gravity and all flowing toward the Great Attractor at its heart. So, case closed. The Great Attractor is simply the gravitational center of the Laniakea supercluster, right, perhaps not entirely. While the mass of the Oumuamua cluster and the surrounding supercluster is immense, some calculations suggest it might still not be enough to account for the full strength of the observed pull. This leads to a haunting possibility. Could the Great Attractor itself be pulled by something even more colossal lurking farther away in the cosmic shadows? There are hints of structures beyond, like the titanic Shapley supercluster, an even greater concentration of mass hundreds of millions of light-years farther on. It may be that the Great Attractor is not a final destination, but a waypoint on a far longer cosmic journey, a single step in a gravitational river flowing toward an unknown, more distant sea. The anomaly, therefore, persists. We have found the visible source of the pull, but the lingering question of whether we have accounted for all of its strength reminds us that our place in the cosmos is defined by motions we are only beginning to trace, pulled by forces whose ultimate origins still lie hidden in the dark. But even our most pristine map of the infant universe seems to hold a strange and perhaps troubling alignment. The cosmic microwave background radiation is the oldest light we can see, a snapshot of the cosmos when it was just 380,000 years old. This faint glow, a nearly uniform bath of microwaves coming from every direction, is the foundational evidence for the Big Bang. By studying its tiny temperature variations, mere millionths of a degree, cosmologists have pieced together the universe's origin story with incredible precision. Yet within this most sacred of datasets, a bizarre pattern emerged, one so unsettling it was given a dramatic name, the axis of evil. When scientists analyzed the largest scale fluctuations in the CMB, they found a perplexing correlation. These ancient hot and cold spots appear to be subtly aligned or correlated with the plane of our own solar system and the direction of Earth's motion through space. This is a direct challenge to the cosmological principle, a cornerstone of modern cosmology which states that the universe on large scales is homogeneous and isotropic. It should have no center, no edge, and no preferred direction. The universe should not care which way the solar system is tilted, yet the data suggests it might. The implications of this are profound. If the alignment is real and not an illusion, it means our place in the cosmos is not random. It hints that the entire observable universe might have a large-scale structure or orientation that somehow connects to our local neighborhood. This is a staggering thought, suggesting a fundamental link between the very large and the relatively small that our theories do not predict. The scientific community has responded with intense scrutiny. The primary defense is that this is a statistical fluke. When you look at any complex dataset, you can sometimes find seemingly significant patterns purely by chance. The human brain is wired to find patterns even where none exist. Perhaps we are simply seeing a cosmic mirage. Others argue it could be a foreground effect, contamination from something within our own galaxy or solar system that hasn't been perfectly subtracted from the CMB data. Dust, magnetic fields, or even the solar system's own motion could be imprinting a faint signal that mimics an alignment. Despite years of analysis with increasingly sensitive satellites from WMAP to Planck, the peculiar alignment stubbornly persists, though its statistical significance remains hotly debated. For some, the axis of evil is a ghost in the data, a problem that will eventually be explained away. For others, it is a genuine crack in the foundation, a whisper that our universe might not be as uniform and random as we have always assumed. It forces a humbling question. Are we seeing the universe as it truly is, or are we, in some subtle and profound way, seeing our own reflection in the cosmic mirror? While the cosmos whispers its largest secrets, a perfect geometric shape has been silently spinning on a world in our own solar system for longer than we have been watching it. At Saturn's North Pole, a hexagon of cloud stands as one of the most visually arresting anomalies in the heavens. This is not a trick of low resolution or a fleeting storm. It is a colossal, six-sided structure, each of its sides longer than the diameter of our own Earth, and it has been there for at least 4 decades, a permanent feature etched into the atmosphere of a gas giant. The Voyager probes first glimpsed it in the 1980s, a strange, angular shadow in the fuzzy images. Decades later, the Cassini spacecraft arrived and gave us a breathtaking, high-definition view of the hexagon in all its glory, a honeycomb-colored whirlpool of clouds spinning with an eerie, precise symmetry. The sheer scale is difficult to grasp. You could fit our entire planet inside one of its sides with room to spare, and the entire structure rotates with Saturn, completing one turn roughly every 10 hours and 39 minutes. What natural force could possibly carve and maintain such a perfect polygon on a planetary scale? The leading clue comes not from astronomy, but from fluid dynamics labs here on Earth. When scientists spin a cylinder of fluid representing a planet's atmosphere at different speeds, they can produce stable polygonal shapes in the swirling vortex at the center. A hexagonal pattern is one of the most common to emerge. This suggests Saturn's hexagon is a giant standing wave, a persistent pattern in the fast-moving jet stream that acts like a permanent atmospheric oscillation. It is the planetary equivalent of a vibration creating a specific, frozen shape in a rotating liquid, but the laboratory models, while helpful, only deepen the real mystery. Those experimental shapes are delicate and transient, lasting only as long as the conditions are perfectly controlled. Saturn's hexagon, by contrast, is a monument of stability. It has endured for generations through the planet's long seasons, unfazed by the churning chaos of the surrounding atmosphere. What provides such unwavering structure? What unknown property of Saturn's deep atmosphere, its rotation, or its internal heat engine locks this geometric wave in place with such unwavering precision? We have searched the solar system and found nothing like it. Jupiter's poles are a chaotic mess of cyclones. Neptune and Uranus show blobs and streaks. Only Saturn presents this stark geometric perfection. It is a reminder that even within our celestial neighborhood, the planets hold unique and profound secrets. The hexagon is a cosmic work of art, a natural theorem written in clouds whose proof we are still desperately trying to solve. The geometric perfection of Saturn's hexagon finds a distant, fiery echo in the depths of our own galaxy. Around the binary star system HD 44179, roughly 2,300 light-years away in the constellation Monoceros, hangs a cosmic structure so bizarre it was named simply for its appearance, the Red Rectangle Nebula. Through the lens of powerful telescopes, it does not look like the classic billowing clouds of the Orion Nebula or the delicate rings of a planetary nebula. Instead, it presents a stark, almost architectural form, a vivid, blood-red rectangle with distinct X-shaped spikes radiating from its blazing central star. This is not an artist's rendering or a trick of perspective. It is a real, glowing object that defies the typically chaotic and fluid shapes we associate with dying stars. The Red Rectangle is a protoplanetary nebula, a fleeting and rare phase in a star's life. This is the brief period, lasting perhaps only a few thousand years, when a sun-like star has exhausted its nuclear fuel and begins to shed its outer layers into space, but its core is not yet hot enough to make the surrounding gas fluoresce brightly. The eerie red glow comes not from the star itself, but from a process called luminescence, where dust grains convert the star's harsh ultraviolet light into deep red visible light. What makes this nebula an anomaly, however, is its shocking geometry. Space is a realm of spheres, spirals, and expanding bubbles, not sharp, angled rectangles. So how does a dying star create a structure that looks like it was drawn with a cosmic ruler? The leading theory hinges on the fact that the central light is not one star, but two, locked in a tight orbital dance. Astronomers believe that as the primary star began its death throes, it expelled vast cones of gas and dust from its poles, a common phenomenon. The key is the binary companion. Its gravitational influence likely sculpted these outflows, funneling the material into two dense, opposing cones. From our vantage point here on Earth, we are looking almost directly at the side of this double cone system. The edges of the cones, seen nearly edge-on, create the illusion of a rectangle's long sides, while the X-shaped spikes are the glowing rims of the cones viewed in projection. Adding to the complexity, a thick, dusty disk likely encircles the binary pair, further constricting the outflow and sharpening its edges into the crisp lines we observe. Yet, for all the elegance of this model, mysteries persist. The symmetry is almost too perfect, the angles are remarkably sharp, and the entire structure appears precariously balanced. The precise mechanics of how the binary interaction, the disk, and the stellar winds conspire to create such a clean, geometric shape remain an active puzzle. It is a celestial sculpture in progress, a snapshot of a star's final artistry, revealing that even in death, the universe can produce forms of breathtaking and precise beauty that challenge our expectations of cosmic chaos. From the precise geometry of distant nebulae, we turn our gaze back to our own planet's orbit, where a modern legend was born. Circling the Earth just beyond the atmosphere, a story persists of an ancient, silent sentinel watching over humanity. They call it the Black Knight satellite, and its tale is a perfect storm of misunderstood signals, strange sightings, and the deep human desire to find patterns in the void. The legend claims this is an alien probe, tens of thousands of years old, orbiting in polar trajectory, a relic from a forgotten visitation. Its origins are as tangled as its supposed purpose. The first thread traces back to the brilliant inventor Nikola Tesla in 1899. While experimenting with his high-voltage radio equipment in Colorado Springs, Tesla reported picking up strange, rhythmic signals he could not explain. He speculated they might be of extraterrestrial origin, a communication from Mars. Decades later, in the 1920s, amateur radio operators reported similar odd echoes, where their own broadcast signals seemed to return to them seconds later, as if bouncing off something unknown in space. These long-delayed echoes remain a curious radio phenomenon, but they were not evidence of a satellite. The next piece of the puzzle fell into place in the 1950s and 60s, at the height of the Cold War space race. Both the United States and the Soviet Union were tracking each other's secret satellites. In this climate of paranoia, unidentified objects on radar were often reported in the press. Several newspapers, including the St. Louis Post-Dispatch and Time magazine, ran stories about a mysterious dark object in polar orbit, which the U.S. Air Force was supposedly tracking. In most cases, these were likely early spy satellites or discarded rocket boosters, their missions classified, their existence shrouded in official secrecy that only fueled public speculation. Then came the photograph that cemented the legend. During the Space Shuttle Endeavour's STS-88 mission in December 1998, astronauts captured an image of a strange, tumbling object against the blackness of space. It had an irregular, angular shape, unlike the smooth modules of the International Space Station they were assembling. This single image, widely circulated on the early internet, became the definitive proof for many. Here was the Black Knight caught on film by NASA itself. The reality, as is often the case, is more mundane but no less fascinating. NASA identified the object as a thermal blanket lost during an earlier spacewalk. These blankets, made of multilayer insulation, are essential for temperature control on spacecraft. When they come loose, they can drift and tumble in unpredictable ways, their silvery layers catching the sunlight to create bizarre, unidentifiable shapes. This perfectly explains the famous photograph, but what about the tracking data, the radar contacts? There is a very real object that sometimes gets labeled as the Black Knight. It is a piece of space debris catalogued as Object 199806099. This debris is a fragment from the Discoverer 8 satellite, a Corona spy satellite launched by the United States in 1959. A piece of its casing or a fixture broke away and has been in a decaying polar orbit ever since. It is a literal black night, a dark, man-made object silently circling the Earth, but its origin is terrestrial, not extraterrestrial. The enduring power of the Black Knight story is not in its scientific validity, but in its cultural resonance. It is a case study in how anomalies are born. It begins with a genuine, unexplained event like Tesla's signals. It grows through misinterpretation and coincidence as secret military projects create a vacuum of information filled by public imagination. It is solidified by a single, compelling piece of visual evidence that has a simple, rational explanation. Finally, it is perpetuated by our innate storytelling drive, the desire for a universe that is not empty but watched. The Black Knight satellite is not an alien artifact, but it is a human one, a modern myth that reveals more about our own hopes, fears, and pattern-seeking minds than it does about any visitors from the stars. The legend of the Black Knight reveals our desire for cosmic company, but the universe offers its own, far stranger candidates without any need for myth. Tabby's star, the original so-called alien megastructure star, continues to defy simple explanation, its light curve a jagged script of mysteries. The most shocking entry in that script arrived on day 792 of the Kepler mission's observations. Without warning, the star's light plummeted by a staggering 15% over just a few days. To grasp the scale, a Jupiter-sized planet would cause a 1% dip. This was the signature of something monstrously large and profoundly irregular passing in front of the star. It was not a single, clean event, but a complex, multi-peaked plunge, as if a swarm of enormous, uneven fragments were tumbling through our line of sight. This was no orderly transit. It was a celestial traffic jam of epic proportions. This dramatic event sits atop an even deeper, slower mystery. By scouring historical photographic plates from over a century of astronomy, researchers made a startling discovery. Tabby's star has been gradually fading for the last 100 years. This long-term secular dimming amounts to a total decrease of nearly 20% of its original brightness. The combination is baffling, a century-long slide punctuated by sudden, catastrophic drops. A single swarm of comets cannot explain a trend that lasts longer than a human lifetime. A planetary collision might create a sudden dip, but not a century-long decline. The star is telling us a story in two distinct chapters, and we are struggling to translate both. This forces astronomers to consider ever more exotic natural scenarios. Perhaps we are witnessing the aftermath of a cataclysmic planetary breakup. A giant planet, or even a dwarf planet, wandering too close to its star could be torn apart by immense tidal forces. The resulting debris field, a chaotic ring of shattered rock and dust, would orbit in clumps and streams, creating the erratic dimming patterns. Over decades, this dust could slowly spiral inward or drift outward, accounting for the long-term fade. Another possibility lies within the star itself. Could Tabby's star belong to a rare, unknown class of variable star, one with internal dynamics so volatile they cause immense, irregular eruptions of star spots or plasma? Perhaps its magnetic field is undergoing monstrous convulsions, temporarily darkening vast portions of its surface in ways we have never before recorded. Whatever the ultimate cause, Tabby's star has already irrevocably changed astronomy. It is no longer a solitary oddity but a prototype. It has spawned its own class of objects, stars with unusual periodicities, or FDUP stars. It taught scientists and the public alike to embrace the truly bizarre in the data. Every time a telescope now catches a star dimming in an unusual way, the first question is this another Tabby star? It has become a cosmic laboratory, a testing ground where we throw our most extreme astrophysical ideas against the wall of reality to see what might stick. The greatest lesson of KIC 8462852 is not that it might be aliens, but that the universe is capable of phenomena so strange they momentarily break our models, forcing us to invent new ones. While Tabby's star writes its mystery in slow, deep fades, other cosmic objects scream theirs in a blinding instant. In 2007, astronomer Duncan Lorimer was sifting through archived data from the Parkes radio telescope in Australia, searching for new pulsars. What he found instead was a spike of radio energy so brief it could have been missed in the blink of an eye, yet so powerful it defied belief. For just 5 milliseconds, a torrent of radio waves slammed into the telescope, a burst of raw cosmic power that had traveled for over 1 billion years to reach us. This was the first recognized fast radio burst, an FRB, and it opened a door to one of the most energetic and puzzling phenomena in the modern universe. In that sliver of a second, this single burst released as much energy as our sun emits in over 80 years. Imagine harnessing the total output of hundreds of millions of stars and focusing it all into a flash shorter than a camera shutter's click. That is the staggering, incomprehensible power of these cosmic events. For years, the Lorimer burst was a solitary oddity. Skeptics wondered if it was a local glitch, a microwave oven door opening near the observatory, or some other terrestrial interference. But then more were found by Parkes and by other telescopes around the world. They were real, and they were coming from deep space far beyond our galaxy. The hunt was on, but catching them was like trying to photograph lightning in a pitch-black room. You never knew where or when the next flash would strike. The mystery deepened with a monumental discovery in 2016. A burst designated FRB 121102 did something extraordinary. It repeated. Unlike the one-off blasts that seemed to be catastrophic final events, this source in a dwarf galaxy 3 billion light-years away fired off multiple bursts, sometimes in frantic clusters. This proved that whatever engine was powering these bursts could survive the event. It was not necessarily a stellar explosion, but perhaps a powerhouse that could turn on again and again. Suddenly, astronomers had a target they could point their telescopes at and watch. They traced the repeating bursts to a specific, tiny region within that distant galaxy. The leading theory for these repeating bursts now centers on magnetars. These are neutron stars, the collapsed cores of dead stars, but with magnetic fields so intense they are a quadrillion times stronger than Earth. A magnetar experiencing a starquake, a sudden cracking of its rigid crust, or a massive magnetic reconnection event, could theoretically unleash a fire hose of radio energy capable of reaching across the universe. In 2020, a magnetar within our own Milky Way was observed producing a radio burst that, while much weaker, shared key characteristics with an FRB. This was a crucial clue linking theory to observation, yet for every answer, new questions erupt. While magnetars are a strong candidate for the repeating bursts, the one-off, non-repeating FRBs may have a different, more violent origin. Could they be the final death cry of two neutron stars spiraling together and merging, or a neutron star being torn apart by a black hole? These catastrophic events would be a one-time only show fitting the single burst profile. And then, of course, the most speculative idea persists in the background. Could such focused, powerful bursts be engineered? An advanced civilization might use a similarly colossal pulse to power light sails for interstellar probes, a beacon whose brief nature is a feature, not a bug. While this is the least likely explanation scientists consider, its very discussion highlights how extreme these events truly are. They push our understanding of physics to the limit. Today, new telescopes like the Canadian Hydrogen Intensity Mapping Experiment, CHIME, are detecting dozens of FRBs every month, mapping their locations across the cosmos. With each new detection, we learn a little more. We know they are cosmological, coming from billions of light years away. We know their signals are dispersed, stretched out by the tenuous gas between galaxies, which allows us to actually weigh the missing ordinary matter in the universe. But the central, fundamental puzzle remains. What natural engine can possibly be so efficient, so violent, and so precise that it can convert unimaginable energy into a radio flash that crosses the universe in the time it takes a nerve signal to reach your hand? We are left listening to the echoes of cosmic explosions we cannot yet see. Each millisecond burst a question mark written in pure energy. The staggering power of a fast radio burst is a testament to a star's violent end, but sometimes a stellar death leaves behind a ghost. Far beyond the brilliant, tangled filaments of the Cassiopeia, a supernova remnant, a faint greenish shell of gas drifts through space. Astronomers call it the green ghost. This ethereal bubble is enormous, located about 50 light-years away from the main remnant, and it is expanding outward at a relentless 700,000 miles per hour. At first glance, it seemed like just another wisp in the interstellar medium, but then scientists looked closer and the mystery began. They analyzed its light and found a shocking signature. The green ghost is not just any cloud of gas. Its chemical composition is a perfect match for the inner layers of the Cassiopeia, a supernova itself. It is rich in oxygen, neon, and other heavy elements forged in the heart of the same massive star. This ghost is a piece of the star that died, but it is telling a different story of that death. The distance and speed tell the tale. For this shell of star stuff to have traveled 50 light-years from the explosion site, it must have been launched not during the final supernova, but thousands of years before the star's cataclysmic end. Imagine a massive star in the final millennia of its life, not simply burning fuel until it collapses, but convulsing. It experiences a colossal pre-supernova eruption, a titanic hiccup that blasts a huge portion of its own atmosphere out into space at incredible speed. The star then somehow holds itself together, continuing to shine for centuries more, while that ejected shell, the future green ghost, races ahead into the void. Only later does the star's core finally give way, triggering the main supernova explosion that creates the Cassiopeia, a remnant we see today. The ghost arrived first. This discovery shatters the simpler textbook model of a supernova, where a star simply runs out of fuel and blows up. It suggests that the final chapters in the life of a giant star are far more chaotic and dramatic than we knew. These pre-supernova eruptions may be common, a hidden phase of stellar evolution where dying stars shed their skins in violent fits before the final curtain call. The green ghost is a fossil of that forgotten prelude, a cosmic echo of a star's first scream long before its last. It forces us to ask what could cause such a premature eruption. Is it a desperate struggle within the star's core as it fuses ever heavier elements? Could it be the influence of a hidden binary companion stirring the pot of nuclear fire? For now, the ghost keeps its secrets, a silent, glowing testament to the fact that even a star's death is not a single event, but a story with many violent chapters. While the green ghost whispers of a star's violent prelude, another visitor arrived without warning, a messenger from the void between stars. In October 2017, the Pan-STARRS telescope in Hawaii spotted a faint point of light moving at impossible speed. It was already on its way out of the solar system, a traveler that had passed closest to the sun weeks earlier. Astronomers named it Oumuamua, Hawaiian for scout or messenger from the distant past. This was the first confirmed object from another star system ever observed within our own, and it was unlike anything we had ever seen. Its trajectory was hyperbolic, meaning it was not bound by the sun's gravity. It was just passing through, a cosmic pebble flung across the galactic ocean. As telescopes around the world swiveled to track it, the data painted a portrait of profound strangeness. First was its shape. By observing how its brightness changed dramatically as it tumbled, scientists deduced its form. It was not round, it was not lumpy. It was wildly elongated, perhaps 10 times longer than it was wide. Imagine a cigar, or more likely a flat pancake, tumbling end over end through the darkness. Natural solar system objects, even asteroids, are not that extreme. Then came the second shock, its motion. As Oumuamua sped away from the sun, something was wrong. Its path could not be explained by gravity alone. It was accelerating just slightly, as if given an extra, gentle push. For a comet, this is normal. Icy comets heat up near the sun, venting gas and dust that acts like a natural rocket engine, creating a non-gravitational acceleration. But Oumuamua showed no coma, no fuzzy envelope of gas and dust, no tail. Our best instrument saw only a bare, rocky-looking speck. It was accelerating without any visible sign of propulsion. The scientific debate ignited with ferocious intensity. One camp argued it must be a comet, but one so ancient and baked by cosmic rays that its surface developed a thick, insulating crust, trapping its ice inside. Occasional, invisible jets of gas from tiny cracks could provide the push without creating a visible cloud. Others proposed it was a new class of object entirely, a hydrogen iceberg. In the cold, dense cores of molecular clouds, pure hydrogen could theoretically freeze. A chunk of solid hydrogen would be invisible as it sublimated, turning directly from ice to gas in sunlight, providing the acceleration and leaving no dusty trail. Yet, such an object was purely theoretical, and many questioned if it could survive the journey through interstellar space. The combination of extreme shape and hidden acceleration, however, led to the most controversial idea of all. Could Oumuamua be artificial? Astronomer Avi Loeb famously suggested its properties were consistent with a light sail, a thin, reflective sheet pushed by the pressure of starlight. A discarded piece of alien technology or a purposeful probe could explain the pancake shape and the solar radiation pressure, giving it an extra kick. The scientific mainstream largely rejected this, arguing it was an extraordinary claim without extraordinary proof, but that very debate was the point. Oumuamua was a genuine anomaly that forced astronomers to stretch their imaginations to the breaking point. It was a data set that defied easy categorization, a reminder that the first example of anything from interstellar space might be the weirdest one we ever see. Whether a bizarre shard of a shattered planet, a fragile hydrogen snowball, or something else entirely, Oumuamua's true nature remains encrypted in the brief, fading signals we captured as it vanished back into the dark. It was a scout indeed, delivering a single, unambiguous message. The galaxy is full of wonders we have not yet begun to imagine. The strange acceleration of Oumuamua was a puzzle of motion, but at the very heart of our galaxy, a different kind of mystery glows with silent, invisible fury. The center of the Milky Way should be a place of darkness, dominated by the immense gravity of the supermassive black hole known as Sagittarius, a star. Yet when scientists pointed the Fermi Gamma Ray Space Telescope toward this region, they saw something astonishing. A colossal, spherical haze of high-energy gamma-ray radiation was shining from the galactic core, an excess of light that our best models of known astrophysics could not explain. This is the galactic center excess. It is not a single point of light, but a vast, diffuse fog, extending for thousands of light years in all directions from the center. This glow is the signature of something profoundly energetic happening on a staggering scale. And the source of that energy has become one of the most heated debates in modern astrophysics. Two compelling and wildly different explanations are locked in a scientific duel. The first possibility is the one that sends a shiver of excitement through the physics community. This spherical haze could be the long-sought-after signal of dark matter annihilation. The theory goes like this: dark matter particles, according to some models, are their own antimatter counterparts. When two of these particles collide, they would annihilate each other in a flash of energy, producing, among other things, gamma rays. The dense concentration of dark matter predicted to exist at the galactic center would be the perfect place for such collisions to occur frequently. The spherical shape of the excess matches the predicted distribution of a dark matter halo. If this interpretation is correct, then the faint gamma-ray glow is not just an astronomical curiosity. It is the first direct glimpse of the universe's hidden architecture, a beacon from the shadow universe of dark matter itself. The second, more conventional explanation is no less fascinating. The glow could be coming from a vast, unseen population of ancient stellar remnants. Specifically, thousands of millisecond pulsars. These are neutron stars that have been spun up to incredible speeds, rotating hundreds of times per second by siphoning material from a companion star. They act like cosmic lighthouses, emitting powerful beams of radiation, including gamma rays. A dense, ancient swarm of these faint, unresolved pulsars in the galactic bulge could collectively produce the exact same diffuse haze we observe. This would be a monumental discovery in stellar archaeology, revealing a previously unseen chapter in the Milky Way's violent early history, when stars formed and died in frantic bursts, leaving behind a graveyard of spinning corpses. So how do we solve this cosmic whodunit? The key lies in the fine details of the light. If the excess is from dark matter annihilation, the gamma-ray signal should be perfectly smooth and symmetric, like a cloud of glowing gas. If it is from pulsars, the haze should actually be speckled, made up of countless individual points of light that are simply too faint for Fermi to distinguish. It is the difference between looking at a smooth sheet of frosted glass and a sheet covered in thousands of tiny, dim dots. Current data from Fermi tantalizingly suggests there might be some speckling, some hint of point sources within the glow favoring the pulsar explanation. But the evidence is not yet conclusive. The next generation of gamma-ray telescopes with higher resolution and sensitivity will be the ultimate arbiters. They will either resolve the fog into a glittering field of countless pulsars or confirm its smooth, shadowy nature. This mystery, glowing silently at the crossroads of our galaxy, holds a dual promise. Its resolution will either unveil the fundamental particle that shapes the cosmos, or illuminate a forgotten era of frenzied starbirth at the dawn of the Milky Way. That faint gamma-ray glow from our galactic center speaks of invisible forces, but a different kind of emptiness reigns in a distant corner of the cosmos. In the constellation of Boötes, the herdsman, lies a nothingness so vast it defies comprehension. This is the Boötes void, a spherical region of space measuring an almost inconceivable 330 million light-years across. To grasp that scale, if you placed our Milky Way galaxy at one edge, the most distant galaxies on the opposite side would be so far away their light would take over 300 million years to reach us, even moving at the speed of light. Within this staggering volume, you would expect to find tens of thousands of galaxies based on the average density of the universe. Instead, astronomers have found only about 60. It is a cosmic desert on a scale that should not exist. The universe, in its infancy, was a nearly smooth soup of matter and energy. As it expanded and cooled, gravity began to pull that material together, creating the vast cosmic web we see today, a network of brilliant galaxy clusters and filaments surrounding immense dark voids. The Boötes void is not just a void, it is a supervoid, a gaping hole in that web so large it challenges our understanding of how structure formed in the first place. According to our best models of cosmology, matter should not have clumped together in a way that leaves a cavity this enormous. It is like stirring cream into coffee and finding not a marbled pattern but a single perfect bubble the size of your cup. The sheer scale of this emptiness forces us to question whether our theories of the early universe are complete, or if some unknown process swept this region clean of nearly all its matter billions of years ago. Yet within this profound emptiness there are a few lonely survivors. The handful of galaxies that do call the Boötes void home are fascinating in their own right. They are isolated, having evolved for eons with few, if any, galactic neighbors. This extreme isolation makes them cosmic laboratories, without the gravitational tug of other galaxies, without the frequent collisions and mergers that shape galaxies in crowded clusters. How does a galaxy grow and change? These void galaxies tend to be smaller, fainter, and often irregular in shape. They are also unusually rich in gas, the raw fuel for star formation, because they have not been stripped clean by interactions with a hot intergalactic medium. Some appear to be forming stars at a quiet, steady pace, like solitary homesteaders tending a private garden, while others seem stunted, as if the very emptiness around them stifled their growth. Studying these isolated systems helps astronomers disentangle the internal processes of galaxy evolution from the external influences of a crowded environment. Each one is a testament to resilience, a flickering candle in a cavern of darkness, holding clues to how all galaxies, including our own, might have begun. The Boötes void, therefore, presents a dual mystery. Its very existence is a profound challenge to our models of the cosmos, a silent question mark hanging in space. And the few galaxies within it are rare books, written in a language of solitude, waiting to teach us how the universe builds its islands of light in the deepest reaches of nothing. While the Boötes void presents a staggering emptiness, a discovery within our own crowded galaxy reveals a different kind of absence, one with immense gravitational weight. Tucked away in the constellation Monoceros, astronomers have found a candidate for the smallest black hole ever detected, and they found it hiding in plain sight by watching a star dance with an invisible partner. They call it the unicorn. This potential black hole lies a mere 1,500 light-years away, practically in our cosmic backyard, and it weighs in at roughly 3 times the mass of our Sun. That size is critically important because it sits right on the mysterious boundary between neutron stars and black holes, in a mass gap where very few objects have ever been found. The unicorn was not discovered by detecting X-rays or a glowing accretion disk, the usual hallmarks of a feeding black hole. Instead, researchers were studying a red giant star, a swollen, aging sun. They noticed 2 peculiar things. First, the star's light periodically dimmed and brightened in a way that suggested its shape was being stretched, pulled into a teardrop by an incredibly strong, nearby gravitational source. Second, the star's velocity was shifting, revealing it was orbiting something massive every 62 days. That something, however, was completely dark. By meticulously analyzing the red giant's distorted shape and orbital motion, scientists could calculate the mass of its invisible companion. The number they got was too heavy to be a neutron star, which typically maxes out around 2.2 solar masses, but it was remarkably light for a black hole, which usually start at around 5 solar masses. The unicorn fell perfectly into that theoretical gap, making it a unicorn indeed, a rare and almost mythical object. If its identity is confirmed, the implications are profound. It would tell us that the corpses of dead stars can exist in a wider range of masses than we thought, filling a crucial gap in our understanding of stellar evolution. Did it form directly from the collapse of a star, or was it a neutron star that later accreted more material? Its discovery also proves a powerful new hunting technique. By searching for stars being subtly stretched and tugged by unseen companions, astronomers can now find quiet, dormant black holes that are not actively consuming matter and emitting radiation. This opens a new window into the dark population of black holes we know must be lurking throughout the Milky Way, silent ghosts we can now find by watching the dances they force upon their stellar partners. The unicorn reminds us that sometimes the most profound discoveries are not about what shines, but about the invisible fingerprints left on the light of others. Far beyond the silent orbit of Neptune, our solar system does not simply fade into the interstellar dark. It is girded by the Kuiper Belt, a vast donut-shaped realm of frozen leftovers from the planetary construction yard. Here, dwarf planets like Pluto and Eris glide among countless smaller icy bodies, a cosmic junkyard holding pristine clues to our system's birth. Yet, as astronomers began to map this distant frontier, they encountered a boundary so abrupt it seemed artificial. The population of these icy objects does not gradually thin out with distance. Instead, it plummets off a cliff. At roughly 50 astronomical units from the Sun, about 50 times the Earth-Sun distance, the number of detectable Kuiper Belt objects drops precipitously. Beyond this line, the vast expected reservoir of primordial ice seems to simply vanish. This is the Kuiper Belt Cliff, and its existence is a direct challenge to our models of how the solar system formed. Standard theory suggested that the primordial disk of gas and dust from which the planets coalesced should have extended much farther out, gently fading at its edges. The objects that formed there should still be there, or at least their scattered descendants should create a gradually diminishing population for hundreds of astronomical units. The sharp cutoff we observe is like finding a bustling city that ends abruptly at a high wall with nothing but empty desert beyond. So what built this wall in our cosmic backyard? One compelling theory points to gravity, but not from anything we can currently see. The orbits of some extreme, detached Kuiper Belt objects already hint at the possible presence of a large, undiscovered planet, often called Planet 9. This hypothetical world, several times the mass of Earth, could orbit hundreds of astronomical units out. Its immense gravitational influence might be acting as a shepherd, not by gathering objects but by violently clearing them out. Over billions of years, its distant tug could have destabilized the orbits of any objects beyond 50 astronomical units, either flinging them inward toward the Sun or ejecting them from the solar system entirely. This would leave behind a sharply truncated belt, a fossilized edge marking the zone of this hidden planet's chaotic influence. Another possibility looks back to the very beginning. Perhaps the solar system's birth cloud, the solar nebula, was not a gently fading mist. It might have had a surprisingly sharp edge itself, like a pond frozen instantly at its rim. If the cloud of material was truncated, perhaps by a nearby stellar neighbor's radiation or tidal pull in the Sun's infant star cluster, then planet formation would have had a hard stop. There simply would have been very little material beyond that boundary to ever coalesce into objects, creating a natural and permanent cliff in the distribution of ice. Each explanation paints a dramatically different picture of our solar system's history. One suggests a still hidden giant, a ghost planet whose gravitational echoes we see in the emptiness it created. The other suggests a more isolated, abrupt genesis, with our entire planetary family born inside a cosmic bubble with definite walls. The Kuiper Belt Cliff is therefore more than a curious statistical drop. It is a forensic line in the ice, waiting to tell us whether we are still missing a major player in our own solar system, or whether we need to rewrite the first chapter of our local cosmic story. That emptiness beyond the Kuiper Belt Cliff defines the edge of our local influence, but what if even the grandest structures we can see are being pulled by something beyond our view? A discovery in the early 21st century suggested exactly that, pointing to a motion so vast it challenges the very definition of our cosmos. Astronomers studying the faint afterglow of the Big Bang found evidence that entire clusters of galaxies are streaming in a coherent direction at incredible speeds, a phenomenon they called the dark flow. This is not the gentle drift of expansion, but a determined rush, as if a cosmic river is pulling thousands of galaxy clusters toward a single point on the sky, far beyond the edge of everything we know. The detection method itself is a masterpiece of cosmic deduction. It uses the kinetic Sunyaev-Zeldovich effect. Here is how it works. As the ancient light from the Big Bang, the cosmic microwave background, travels through the universe, it occasionally passes through the hot gas that surrounds massive galaxy clusters. If those clusters are stationary relative to the expansion of space, the interaction simply scatters the light in a known way. But if a cluster is moving, it gives the passing light a slight kick, a Doppler shift, imprinted like a fingerprint on the microwave radiation. By meticulously mapping this subtle distortion across hundreds of distant clusters, researchers led by Alexander Kashlinsky claimed to see a pattern. The clusters were not moving randomly. They appeared to be streaming together at velocities of up to 1,000 kilometers per second toward a region in the constellations Centaurus and Vela. The scale of this motion is the true anomaly. Gravity, as we understand it, is a local phenomenon. The pull of a massive object weakens with distance. The known mass distribution of the entire observable universe, with all its galaxies and dark matter, should not be able to create such a coherent, large-scale flow. There is simply not enough stuff in one direction within our cosmic horizon to explain the tug. This leads to the most provocative and mind-bending implication of all. The dark flow could be the gravitational signature of something lying outside our observable universe. Think of our cosmos not as everything that exists, but as a bubble of space-time we can see, limited by the distance light has traveled since the Big Bang. The dark flow suggests that beyond this bubble's edge, in the unobservable realms, there exists a colossal concentration of mass so immense its gravity reaches across the void to pull on everything inside our horizon. In the language of theoretical cosmology, this could be evidence for a multiverse. Our universe might be one bubble among many in a vast cosmic foam, and the gravitational pull of a neighboring universe forever beyond our direct sight could be the unseen hand guiding this dark river. Unsurprisingly, such a radical claim is met with intense skepticism and debate. Other teams analyzing different data have failed to confirm the signal, arguing that the statistical methods used could produce a false pattern from noise or foreground effects. The controversy highlights the extreme difficulty of measuring such a subtle effect at the very limits of our observational capabilities. Whether the dark flow is a genuine anomaly or a statistical phantom remains unresolved. Yet its mere proposal forces us to confront a staggering possibility. The ultimate structure shaping the motion of galaxies may not reside within our universe at all, but in a realm forever hidden by the ultimate horizon, a reminder that the greatest forces may always lie just beyond the edge of our understanding. The profound strangeness of Oumuamua was thrown into even sharper relief just 2 years later. In August 2019, Crimean amateur astronomer Gennady Borisov spotted a new visitor with a telltale fuzzy glow. This was 2I/Borisov, our second known interstellar guest, and it was everything Oumuamua was not. As it swung around the sun, 2I/Borisov sprouted a magnificent, streaming tail of gas and dust. Its chemistry, its behavior, its very appearance were textbook, a completely ordinary comet, just one born around another star. This normalcy was itself a revelation. It proved interstellar space is indeed filled with icy wanderers, just as we always expected. But that very normalcy made Oumuamua's bizarre profile even more confounding. If interstellar objects are common, why was the first one we saw so utterly weird? This contrast forced scientists to dig deeper into the nitrogen iceberg hypothesis. Imagine a distant Pluto-like world orbiting another star. This exo-Pluto would be rich in frozen nitrogen, a volatile ice that sublimes easily. If such a world were ever shattered by a colossal impact, fragments of its nitrogen-rich crust could be flung into interstellar space. A chunk of this material, perhaps a few hundred meters thick, tumbling toward our solar system, would explain everything. As it approached the sun, the intense heat would cause the solid nitrogen to vaporize directly from its surface. This outgassing would be clean, producing no reflective dust, accounting for the lack of a visible coma. The gentle jetting of nitrogen gas from the sun-warmed side would perfectly explain the mysterious non-gravitational acceleration. Even the object's shape fits. A slab of nitrogen ice eroding unevenly under the sun's rays could naturally assume a flattened, pancake-like form. It is an elegant, if still speculative, solution that requires no new physics, only a new type of object from an alien planetary system. Yet confirming such a theory for Oumuamua is now impossible. It is long gone, a fading memory in our telescopes. This painful truth highlights a monumental technological challenge. These interstellar scouts pass through our system at incredible speeds, giving us only weeks or months to study them. To truly solve such mysteries, we need to be ready to chase one. Scientists are now designing missions like the European Space Agency's Comet Interceptor, which will lie in wait at a gravitational parking spot, poised to sprint toward the next intriguing visitor. More ambitious concepts envision spacecraft propelled by powerful lasers, capable of matching velocity with an interstellar object and flying alongside it for years. The dream is to get a close-up look to touch and taste a piece of another star system. The very existence of Oumuamua and its ordinary cousin Borisov forces a profound shift in perspective. The cosmos is not just full of things we have categorized, it is brimming with things we have not yet imagined. Anomalies like these are not errors in our data. They are corrections to our imagination, proof that the universe's catalogue of wonders is far stranger and more diverse than any list we have yet written. Even the very atoms that build our world are part of a cosmic shortfall. While dark matter and dark energy dominate the universe's budget, a more intimate mystery haunts the ordinary stuff of creation. The protons and neutrons called baryons that form every star, planet, and person. We have a precise ledger from the dawn of time. The afterglow of the Big Bang tells us exactly how much of this normal matter should exist today. Yet when astronomers add up everything they can see, all the glittering galaxies, the swirling clouds of cool gas, the dusty nebulae, the total comes up shockingly short. Nearly half of all the baryonic matter that should be here is simply missing. This is the missing baryon problem, and it is not a small accounting error. It is as if you meticulously counted every grain of sand on a beach, only to realize half the sand from the original shipment has vanished into thin air. The universe has misplaced the building blocks of itself. The hunt for this lost material led scientists to a startling realization. Perhaps the atoms are not missing at all, but hiding in plain sight, transformed into a state so elusive it had escaped our detection. The leading theory points to the vast, empty expanses between galaxies. These cosmic voids are not truly empty. They are thought to be threaded with an incredibly thin, searingly hot fog of gas, a web of matter so diffuse it is nearly invisible. This is the warm, hot intergalactic medium, or WIM. Picture steam rising from a pot of boiling water, a wispy, pervasive haze that fills the kitchen but is difficult to see unless the light hits it just right. The WIM is like that, but on a cosmic scale. It is gas heated to temperatures of millions of degrees, not by starlight, but by the violent gravitational shocks that occurred as the universe's large-scale structure formed. At such extreme heat, the gas does not glow in visible light. Instead, it reveals itself only by the faintest fingerprints it leaves on light passing through it. Detecting this phantom fog is one of astronomy's greatest technical challenges. To find it, scientists use distant beacons called quasars, the brilliant cores of active galaxies billions of light-years away. As the quasar's intense light travels across the universe toward us, it passes through these filaments of hot gas. Atoms within the WIM, like oxygen and neon, absorb very specific wavelengths of that light. The result is a series of extremely faint absorption lines etched into the quasar's spectrum, like a barcode imprinted by the invisible medium. Isolating these lines from the blaze of the quasar's own light is like trying to hear a single, soft whisper in a roaring hurricane. It requires the most sensitive space-based telescopes, like the Chandra X-ray Observatory and XMM Newton, designed to see the high-energy X-rays that this million-degree gas emits. Piece by piece, these observations are beginning to map the shadowy architecture of the cosmic web, finding the predicted tendrils of hot gas stretching between galaxy clusters. The evidence suggests that a vast reservoir of matter is indeed there in the form of this diffuse intergalactic plasma. It appears we have found where the universe stashed its missing atoms. Solving this accounting mystery does more than just balance the books. It reveals the true nature of the cosmos we inhabit. The sparkling galaxies are not isolated islands, but dense knots in a grand, interconnected tapestry. Most of the ordinary matter in the universe exists not in those brilliant knots, but in the dark, hot filaments that connect them, a vast, unseen ocean in which the galaxies float like ships. This changes our understanding of cosmic ecology. This hot intergalactic medium is the reservoir from which galaxies form and into which they eventually recycle their material. It is the circulatory system of the cosmos. The hunt for the missing baryons, therefore, is not just a technical puzzle. It is a quest to complete the map of our home, to understand the full ecosystem of matter, from the densest stars to the most elusive gas between the worlds. It proves that even the familiar stuff of creation can hold profound secrets, hiding in the hottest, most tenuous corners of the void. A streak of light against the cosmic dark is rewriting the story of how black holes can shape galaxies. The Hubble Space Telescope captured an image that at first glance seemed to show a simple scratch on the photographic plate, a thin, brilliant line streaking across a field of galaxies. But this was no artifact. This was a cosmic wake, a trail of blazing blue stars over 200,000 light-years long. And at its tip, the potential source of this incredible violence, a supermassive black hole apparently running for its life. The object, catalogued as RCW103, is moving at such a breakneck speed that it could travel the distance from Earth to the Moon in just 14 minutes. Behind it, the linear feature glows with the hot, young light of infant stars, a stellar contrail left in the black hole's chaotic path. The leading theory for this runaway engine is a story of celestial billiards on the grandest possible scale. Imagine two galaxies, each with its own central supermassive black hole, colliding and merging. Their black holes would eventually sink to the new galaxy's core and begin a slow, spiraling dance destined to merge themselves. But introduce a third player. If a third galaxy had merged earlier, bringing its own black hole into the mix, you would have a chaotic three-body gravitational interaction. In such an unstable system, one of the black holes can be violently ejected, slingshotted out of the galactic core at a significant fraction of the speed of light. This is precisely what astronomers believe may have happened. The ejected black hole, robbed of the vast reservoir of gas it once fed upon in the galaxy's heart, now flies through the thinner intergalactic medium. As it plows through this diffuse gas at supersonic speeds, it compresses and shocks the material in its path. This compression triggers the collapse of gas clouds, igniting a chain reaction of star formation directly behind the speeding singularity. The black hole becomes a cosmic plow, tilling the void and sowing a line of stellar seeds in its wake. There is, however, a more conservative interpretation of the data. The brilliant streak might not be a trail of new stars at all, but a jet of relativistic particles being shot from the poles of a stationary but active supermassive black hole. If this jet is pointed almost directly at us, a side effect of relativity can make it appear brighter and more linear. In this scenario, the black hole is not running away. We are simply looking down the barrel of its most powerful engine. Yet even this explanation requires a rare and extreme alignment. Whether a gravitational cannonball or a perfectly aimed celestial lighthouse, the phenomenon pushes our understanding of black hole behavior to its limits. It shows us that these cosmic monsters are not always stationary anchors at the center of galaxies. They can be set in motion, becoming rogue agents whose violent passage can paint the darkness with unexpected light, forcing entire strings of stars to ignite in the desolate spaces between galaxies. That phantom trail of stars is a testament to violent motion, but our oldest map of the cosmos shows a different kind of disturbance, one frozen in time. Within the faint glow of the cosmic microwave background, the baby picture of our universe, lies a region so profoundly cold it stands out as a cosmic bruise. This is the CMB cold spot, a circular patch in the constellation Eridanus that is significantly cooler than the surrounding sky. Its size is staggering, nearly 1 billion light-years across, and its temperature deviation is so extreme that the odds of it appearing randomly in a statistically uniform universe are less than 1 in 200. It is an anomaly that refuses to be smoothed away by our best models. To explain such a large, cold region, astronomers first turned to a fascinating gravitational effect. When light travels through the expanding cosmos, it climbs in and out of the gravitational wells created by massive structures like galaxy clusters. Normally, the energy lost climbing into a well is regained when climbing out. But if the universe's expansion has accelerated significantly during the photon's journey, as it has due to dark energy, the well effectively becomes shallower by the time the light exits. The photon emerges with a net loss of energy, appearing slightly cooler or redder than it started. This is the integrated Sachs-Wolf effect. A vast, underdense region of space, a cosmic supervoid, would create a perfect scenario for this. Light entering the void would lose energy climbing out of the surrounding dense regions, then, traveling through the near emptiness inside, would find the gravitational landscape flattening due to acceleration, robbing it of the chance to regain that energy. It would exit cooler, creating a cold spot on the CMB map. The logical next step was to look for the void. Astronomers pointed their telescopes toward the cold spot's location, mapping the three-dimensional distribution of galaxies. They found voids, certainly. The universe is filled with them, but none were nearly large or empty enough to account for the profound temperature drop we observe. The largest void found in that direction is immense, but still only about a third the size needed, and its density is not sufficiently low to produce the cooling effect. The evidence for a supervoid explanation simply does not add up. With the most straightforward answer failing, we are left with more extraordinary possibilities. One of the most compelling and mind-bending ideas reaches back to the universe's first fraction of a second. During the period of cosmic inflation, when space-time expanded exponentially faster than light, our entire observable universe is thought to have blown up from a single quantum bubble in a much larger, perhaps infinite multiverse. If another such bubble universe existing in a higher dimensional landscape collided with our bubble during this inflationary phase, the immense energy of that collision could have left a permanent imprint on our cosmos. The cold spot could be the cosmic scar from that primordial encounter, a bruise on the CMB where our universe brushed against another reality. While this multiverse hypothesis is highly speculative and difficult to test, its very consideration underscores the profound nature of this anomaly. The cold spot is not just a statistical fluke or a missing void. It is a feature on our most fundamental map of reality that points to either a gap in our understanding of large-scale structure or to a horizon of physics beyond our current reach. It sits at the crossroads of cosmology and metaphysics, a cold, quiet circle on the sky that may be the closest thing we have to a fingerprint from another universe. From a single, unexplained signal to a cold spot on the edge of reality, these 25 cosmic head-scratchers form a map of our ignorance. They are not errors in the data or failures of our science. They are its very lifeblood, the frontiers where true discovery begins. Each anomaly, from the geometric clouds of Saturn to the phantom pull of the dark flow, is a signpost pointing beyond the edges of our current textbooks. They humble us, revealing not a tidy, solved universe, but a vast and wonderfully weird cosmos still writing its own rules. These mysteries remind us that the greatest chapters of astronomy are not the ones we have memorized, but the blank pages waiting to be filled. So we turn the question to you. Which of these cosmic puzzles captures your imagination the most? Is it the silent, enduring hexagon, the ghostly tug of the Great Attractor, or the haunting possibility of a multiverse bruise? Share your thoughts in the comments below, and if you enjoyed this journey to the edges of understanding, subscribe for more deep dives into the universe's greatest mysteries. Wherever you are, take a moment tonight to look up. You are not just staring at points of light. You are gazing at a living puzzle, an endless story of questions waiting for their answers.